Yeah, just wait, Abhijit. Once we go live, then.
Okay, just let me know.
Yeah.
Hello to everyone.
Hello, sir. Nice to see you.
Oh, thank you.
Yeah, I think it is live now, Abhijit.
To all of you, all the participants of this 9th on monthly lecture series of IASTA. So nothing to say more about IASTA. Still, very briefly, if I want to say about IASTA, that is an so it's a professional organization, as we all know, for all the scientists and engineering community, those who endeavor to advance the aerosol research in the Indian context. And this association, it provides a platform for exchanging knowledge and the know-how, the information among the researchers, member organizations, and related disciplines by organizing conference, technical meetings, lectures, publication, etc. So with the mission, it provides a means for the exchange of scientific knowledge and resources for the advancement of aerosol science. And it is visioned in such a way to find new ways and promoting their existing functionary towards the advancement in the field of aerosol research. So this is, this year we organized probably, I don't know the number, 16th or 17th IASTA conference that was held in Mumbai during 12th to 14th September. And thanks to all the members of the IASTA, including the executive committee members, who had put untiring effort that brought the grand success of this conference. So today, in this 9th monthly lecture of IASTA, I'm happy to say that we have got the renowned scientist Dr. Ratnam from NARL. So he doesn't need an introduction still. Very briefly, if I want to talk about Dr. Ratnam, he is a scientist at NARL, National Atmospheric Research Laboratory. And he has been carried out research in frontline areas like atmospheric science. And before joining NARL, he worked as a postdoctoral fellow and scientist and visiting scientist at Taiwan, Germany, and Japan during 2001 to 2006. And right now, he is leading Aerosol Radiation and Trace Gases Group at NARL. And his major interests are middle atmospheric structure and dynamics, aerosol, radiation, and trace gases, long-term trends, and climate change. And he has generated several experimental campaigns in collaboration with several national and international institutes, including NASA, to address several issues related to atmospheric science. He published more than 250 number of research papers in highly peer-reviewed journals. And 16 students have already been awarded who has worked under Dr. Ratnam. And in recognition of his outstanding scientific contributions, he has received several awards, including prestigious Japan Society for Promotion of Science Award, Best Paper Award at National and International Conference and Workshops, and Nasi Scopus Young Scientist Awards for the year 2010 in Art Science. He became fellow of Andhra Pradesh Academy of Sciences. He is a life member of several prestigious societies like IETE, IMS, ISCA, ISTF, etc. And he is a member of several high-level scientific and technical committees at national and international levels. And he was appointed as a scientific discipline representative from India for international costing. Recently, it's a very proud moment it was for all of us that he has received Indian prestigious award, Shanti Swarup Bhatnagar Award for the year of 2018 under Earth, Atmosphere, Ocean and Planetary Science field from Honorable Prime Minister of India, Mr. Modi ji. And very recently, he authored a textbook on terrestrial atmosphere and ionosphere Physics and Experimental Techniques, jointly with Professor B.V. Krishnamurthy, which is very useful for undergraduate, postgraduate, as well as the research scholar, including early career scientist. So Dr. Ratnam is here with us, and he will be talking on trends and variability of aerosols and trace gases in Asian Summer Monsoon Anticyclone. So, Dr. Ratnam, the stage is...
Okay. Thank you, Dr. Abhijit Chatterjee, for nicely introducing me. And before I start my presentation, I would like to thank Dr. Neeraj Rastogi, who has invited for me for this talk, and also thank Manish for bearing with me. And I'm going to share the screen now. Is it visible?
Yes.
Are you able to see?
Yeah.
Yes, yes.
Okay.
Yeah.
Okay. I'm hope you might have seen me, and I know I can stop my video for sake of saving the brand. Okay. Okay. Thank you. And now I'll be talking about trends and variability of aerosols and trace gases in Asian Summer Monsoon Anticyclone. And before I start my talk, I also would like to thank my colleagues, Dr. Basha, Dr. Hemant, Dr. Akhil Raj, and Dr. Ravindra Babu, who has worked for as a team for this, whatever I'm going to present for next half an hour or so. And also my acknowledgements to Dr. Jean Paul from NASA, who has helped a lot in making realize that battle campaigns.
Introduction now stage is yours.
Hello.
I think some crosstalk.
Hello. Yeah. Am I audible now?
Yes.
Okay. So here I'll be talking more about the some Asian summer monsoon anticyclone and how it is going to affect our pollutants in that region. So this is my outline. So first I'll be talking about Indian summer monsoon system and its circulation. And immediately I'll move to this Asian summer monsoon anticyclone and its variability. And here I'll be touching upon different modes that are present in asthma, that is Asian summer monsoon anticyclone, and how the different monsoon activity like active break or good and bad monsoon or ENSO or El Nino or La Nino, how is going to affect the asthma. And in turn, with this variability, how the trace gas distribution within asthma and from where these trace gases will be entering into asthma, I'll be talking about that. And also vertical variability within asthma during different modes. And then I will move to the next topic like aerosol distribution within asthma. And here I'll be talking about spatial asymmetry within the asthma and long-term trends. And immediately I will move to the next topic that asthma aerosol from balloon campaigns, where we obtained for the first time optical, physical, and chemical properties. And finally, I'll conclude with my summary and future scope. Now, coming to the brief introduction to the monsoon system. In fact, this figure I have taken from Krishnamurthy and Bamble published 50 years back. It's a classic paper where they have introduced very nicely that all the elements of Indian summer monsoon system. It is well known that it is very complex system, but very systematic. In fact, it has in this paper they have mentioned about 9 elements which are very very important for to understand anything related to monsoon system. And first and foremost comes to the monsoon trough, then comes to the masculine high, and third one with the low level jet, then Tibetan high. This is what our particular interesting topic right now. Then tropical jet present at the 100 hectopascal. And at the same time, there will be a lot of monsoon cloud cover and also convection prevailing during this time. And more important, that monsoon rainfall is a final product of this one, where we are interested for many applications like agriculture sector or this thing. And at the same time, we should understand dry static stability and moist static stability pertaining, it means particular for this monsoon system. And these 9 elements are going to play important role in Indian summer monsoon circulation system. Among these 9 elements, I have chosen that 5 elements here, that is monsoon anticyclone 100 hectopascal. You can see it is happening at the top of the atmosphere, I mean troposphere. Then at the same time, there will be tropical state persisting at 100 hectopascal. This is another important aspect where lot of attention is required for the people addressing the aerosols or trace gases in the asthma region. Then cloud cover conversion is another important aspect where the boundary layer pollutants can reach to higher altitudes, and tropical low level jet. It's also called as it will be eastward propagating jet at 850 hectopascal, and these jet can bring lot of pollutants to the Indian region, and this cloud cover or convection can take those pollutants and trace gases to the higher altitudes to the monsoon anticyclone. Of course, monsoon rainfall also plays an important role in removing some of these pollutants from the atmosphere. And just moving immediately to the next, means from this classic paper to the observation, here I show these four elements. I am not showing the monsoon rainfall for the time being, but I'll be talking about it at later stage. But these four important elements of monsoon system is shown here. First and foremost, I was mentioning that low level jet at 850 hectopascal. You can see that strongest that low level jet will be over Arabian Sea, and this is towards eastward, and most of the pollutants can this low level can bring and to the over the Indian region. In fact, there will be if you come to the this is over ocean, it will be 850 hectopascal will be strongest, whereas you come to the land, 700 hectopascal also will be the strongest mode. So within that boundary layer, we can see that most of the transported these pollutants can transport it over the Indian region through the low level jet. At the same time, at 100 hectopascal, close to 16-kilometer altitude, there will be tropical jet persisting, and it's a westward propagating. And if you can see, and there will be, it is exactly over the southern part of India, stretching from 5 to almost 25-degree north. This will be persisting, but only during the monsoon system. At the same time, little higher from 20-degree north onwards, you can see that anticyclone persisting from the Middle East almost to the east part of China, and it is a consistent feature. More or less, in fact, these 4 years from Indian summer months like June to September, these features will be persisting with a maximum amplitude during the July and August. At the same time, you can see the cloud fraction over the headway of Bengal and eastern part of India. These pollutants, for example, any pollutant bringing from low-level jet or Indian region, because of this deep convection, they can be pushed into the higher altitudes. And once it enter into the anticyclone, they'll be persisting for almost like 3 to 4 months. So this is one of the important aspects we should understand before addressing the trace gases or the aerosols present in the Asian summer monsoon anticyclone. So once enter into anticyclone, there are only two ways to that any pollutants can be removed from this anticyclone. One way is the brevet option circulation, that east-west circulation, and another is is a Walker circulation, that is east-west circulation, and another is a BD circulation from north-south circulation. So these are the only two ways where that pollutants can be removed from this asthma. Now, since before going to the details about the trace gases in the asthma, it is very important to characterize the asthma, because any small change in the asthma, it is going to reflect in the trace gases and also in the aerosol. So first we'll be talking about anticyclone itself. So before that, if you plot any satellite measurements, for example, any trace gases or aerosols, as I mentioned, 100 hectopascal is represented for the anticyclone. And this is the figure which you are going to see. And the leftmost panel, this is for the ozone. You can see that without mentioning where is the asthma is located, you can clearly see that low concentration of ozone persisting at 100 hectopascal over Indian region. And in the right side, you can see the carbon monoxide, very high concentration of carbon monoxide at 100 hectopascal, and at the same time, high concentration of water vapor. This gives an indication that the air entering into the asthma is basically from the tropospheric origin, because in the troposphere, more water vapor will be there and more carbon monoxide, and tropospheric air has less ozone. So this gives an indication that this air is being pumped to the anticyclone is basically from the tropospheric origin. At the same time, if you can see that aerosol part, this is from the calypso, and it is very clear that these aerosol also behave like anticyclone, means that it will stretch from enhanced aerosol concentration right from Middle East to the eastern part of China, covering from this almost like Indian region, almost up to the Tibetan high. So these are all just like, without mentioning that this anticyclone persistent, but if you plot somebody will plot like this, it looks like that. Then how this is going to vary, whether it is going to vary with asthma, which is like whether, and how it is going to behave during different phases of the monsoon, like active and break, or good monsoon or bad monsoon, how the ENSO is going to affect these things. In turn, how these will be affected by the trace gas and the aerosols, that will be my next topic. So now first we'll see that how the asthma itself is varying. In general, this asthma will be defined based upon geopotential height. This is a typical, means vertical coordinate height, which is adjusted to the gravity. And typically it varies from 16.75 to 16.9 kilometer. And this contour shows that this anticyclone will be persisting in the both from the right from 22.5 degree north to 40 degree north, and from 25 degree east to almost like 120 degree east. And you can see that this asthma can be divided into four sectors. One is northeast and southeast, or northwest to southwest. But being center of this anticyclone is the lowest, means low, very low, means the highest geopotential height and the lowest wind speed we can expect. So then we subjected last 50 to 60 years of data of this ERA 5 or also MERA 2 and also NCEP ERA NCAR data set to see that there is whether any change in this geopotential height. And the right figure shows that this is a long-term trend, 50 years trend. It is very interesting to see that at the center of the asthma, there is no big change, whereas at the edges of the asthma, particularly the north part and east and west part, you can see the drastic increase in the asthma geopotential height. So this tells that in the warming climate, more that the extent of the asthma is going to increase, and if any change in the asthma, the extent of asthma, that much air pollution or the aerosols or trace gases are going to enter, and that is going to have a different radiative forcing at that altitude, because it is going to persist for more than 3 months altogether during monsoon season. Then in the down figure, we show the zonal wind is the average of all this asthma, complete asthma. You can see that almost the zonal wind has made double in the last 50 years, means it tells that the anticyclone strength is going to increase. It's already seen in the last 50 years, it is almost doubled. And we are expecting the same tendency to increase, and this is having a profound effect in the future climate. So then this is the variability of the asthma. Then how this asthma will vary among the different phases of the monsoon. For example, it has active and breakfast. In fact, you can see the rainfall will not be continuous over central part of India and the most part of India during the monsoon system, where it has some 7 to 10 days of active and break phases will be coming. And we separated the GPS altitudes during the active days and break phase. And this figure shows the climatological features of active and break phase. And this active and break phase is defined by IMD, the same definition we use. And you can see that during the active phase, the asthma is extended asthma, you can see, where in the break phase, it is little contraction was there. The same feature we have seen in the good monsoon and bad monsoon. In fact, in good monsoon, the extension of asthma is more when compared to bad monsoon. And during the El Nino, it is stronger when compared to the La Nina. And this is, in fact, any change in any of these, as I mentioned in the 9 elements in my introduction slide, for example, the change in the static stability or the temperature background, that is again going to affect several parameters of monsoon element. And here we show that the latitude and height variations of these temperature perturbation. And this two lines shows the cold point and last tropos altitude, the latitude wise. In the right panel, it is longitude wise, cold point and last tropos altitude. You can see between 30 to 50 degree north, that the warmer temperature anomalies, and the counterpart in the western side, you can see that in the southern side, you can see that the cold anomalies. Whereas in the eastern part of India, you can see that hard warm anomalies up to even to 10 to 12 kilometers, and in the western part, it is the cold anomalies will persist. And if we move to the how these trace gases will behave during the active and break monsoon or stronger weak monsoon, here I am showing the one typical example. This is the climatology of both strong, the difference between strong and weak monsoon years. First panel is for water vapor, second is carbon monoxide, and third one is the scattering ratio. This is from Calypso. You can see that during the strong monsoon years, the enhanced water vapor is there, almost like it is double the water vapor when compared to the weak monsoon year, and same with the carbon monoxide and same with the aerosol. If you see that the vertical wind, this represents the vertical transport of any pollutants from boundary layer to the utilized region or asthma, you can see right from 70 degrees to 100 degree east, the strong vertical velocity. This is the pressure vertical velocity. It's negative means the upward draft, and if the positive means it's a downdraft. You can see that right from surface to almost 200 hectopascal, the updraft prevails, and any pollutant entering into any of these altitude region, either through low level jet or tropical jet, this is going to enter into the asthma region. And again, if you see that the convection, OLR is proxy for convection, you can see that over the head bay of Bengal, the deepest convection happens The magenta color shows that the 220 the watt per meter square contour. And you see almost in the head of Bay of Bengal in this part of India, this strong convection prevails. As a result, you can see that vertical graph, the vertical wind is showing the updrafts, and in the western side of the India, you can see that the dry atmosphere or the clear sky, where you can see the downdrafts here. So this has a lot of implication in the redistribution of the pollutants entering into the asthma. Now we will see that how this asthma behaves during the ENSO events. For example, in the 2015, there was the strongest ENSO happened, and during that time, we show here in July and August at 100 hectopascal, the top panel, you can see that asthma it is split into two in the month of August. In fact, in general, we should see from Middle East to the eastern part of China, but during the ENSO period, it is split into two. Even the geopotential height, you can see that very low geopotential height is occurred in the when there is a split in this asthma region in the both the eastern edge and the western edge. And as a result of these changes in the asthma, this trace gases also has behaved the same way. Here you can see that percentage difference between the El Nino and La Nino we plotted here. The first panel is for the ozone, and the middle panel is for carbon monoxide, and the bottom panel is for water vapor change. It is a change kept in the percentage. And this black, the black color shows that in general the climatological features of asthma. It is a 16.75 geopotential height. But if you see that white part, that is happened during the ENSO period 2015. You can see that in in all the three panels, the split in the asthma. At the same time, in fact, in general, we are expecting, as I mentioned in my introduction slide, that we will expect low ozone in the asthma region, because it is like a tropospheric air where it is concentration of ozone is less. But to our surprise, you can see that during the strongest ENSO event happened in 2015, the more ozone is seen here. So it tells that the tropospheric air has not entered during the ENSO region, but it is a lower stratospheric air that is being trapped in the asthma region. But at the same time, you can see that carbon monoxide and water vapor, there is a decrease in carbon monoxide and water vapor. This is again, you can treat that as a tracer of troposphere. You can see the less. So it tells that during the ENSO events, the pollutants, the what we thought that the tropospheric air entering into the lower stratosphere is quite opposite, where the lower stratospheric air has entered into the asthma region. So the modes of different asthma and during active and different phases of the monsoon season, it is very important to consider before when we are considering anything related to trace gas aerosols in the asthma region. Then we'll move to the different modes of asthma. Here what we want to show is it has three different modes, particularly depending upon for example, that maximum GPH altitude we have picked up in each day. Means it has, for example, every 0, 6, 12, 18 UTC, we have the data from ERA5 or MERA2. Those days we picked that minimum or maximum geopotential height that is shown in this as the green dots. And when the number of occurrences, if you see, it is mostly coming from 62 means mostly concentrated between almost like 30 to 120 degree east, and the latitudes comes from 25 to 35 degree north. So this is the region where then we segregated the centers of those geopotential height maximum. And when we segregated, you see the right panel, this is the climatological feature, where the center is moved to the western side of India, that we call Iranian plateau mode, and the center of the asthma, that maximum geopotential height, moved to the east part of India, that we call Tibetan mode. And there is other mode which the center of this geopotential height is almost like in elongation mode. So these are the typical three modes. Of course, there are some other modes are also being reported in recent days, but these are the major, almost like 90% of the time you can see this asthma behaving either in the IP mode, TP mode, or in elongated mode. And as a result, what happens, if you plot again those trace gases while separating the IP mode and TP mode and elongated mode, you can see that this slide tells that exactly whatever the modes in the asthma we see, those trace gases as being the same exactly. For example, in the IP mode, you can see that in the western part of India, you can see that high concentration of CO and very low concentration of O3, and also in the high concentration of water vapor. If you see that in the Tibetan mode, that's quite opposite, that the eastern part of the asthma will become stronger. So when somebody is calculating the radiative forcing due to these trace gases, they should keep in mind that you cannot take that complete asthma as a whole to calculate the radiative forcing, because you will end up in the wrong calculation. So this kind of mode is very important to differentiate before calculating any radiative forcing due to these trace gases. Then we'll move to the aerosol part. Here in the aerosol part, we use the calypso. It gives very good information right from surface to the almost like the 20 kilometers altitude. And here in this plot, again we show that the same that anticyclone feature 16.575 geopotential height we show it here, and the down panel we show that the calypso observed the backscatter ratio or extinction in the asthma. You can see that though asthma is restricted from right from 20 degrees to 40-degree north, you can see that aerosols are not uniformly distributed. There is a lot of huge asymmetry in the distribution of aerosols we can see. And this magenta, the contrast shows that the deepest convection happening based upon OLR as a proxy. And you can see that head Bay of Bengal and this part of India, there is a deep convection happening. But only at those places where the deep convection is seen, at that place only we can see the enhancement in the aerosol, but it's not uniformly distributed. And we can see that huge asymmetry in the spatial distribution of aerosol, unlike the trace gas distribution what we see in our previous slides. Then we try to segregate with respect to latitude belt, because we can see the low east part and west part how it is varying, and also the north and south how the spatial asymmetry is coming. Then we have used the cloud side data to see that to get the cloud fraction. And also before that, we can see that in the 27 to 32 degree north, you can see that in the southern part of this asthma is particularly the southeast is more dominant when compared to southwest, but is more dominant when compared to north part of asthma. So this tells that there is a huge asymmetry in the vertical distribution, not only the 100 Pascal, but also in the vertical distribution in the asthma. And one can see that 18 kilometers is the maximum aerosol layer we can expect in the asthma region. Now we again use the same data set, and this time we use the cloud set data to see that whether what is the role of convection in making in transporting these boundary layer pollutants or the aerosols to the utility region. And here we show in the right panel the cloud fraction obtained from the cloud set is almost like long-term data. One can see the deep convective clouds is shown in the altitude profile, where the reflectivity, cloud reflectivity greater than minus 25 dB has been selected. And you can see the cloud fraction right from almost like 2-3 kilometers to almost touching up to 15 kilometer altitude. And when we separated the asthma into 4 regions like southeast, southwest, and northwest, and you can still see that southeast and this magenta color and the black color, that northeast, is having a lot of cloud fraction when compared to the western part of this asthma. At the same time, it's a more interesting thing that the down panel, this vertical wind is showing here. And you can see that in the southeast and northeast part, only that you can see that negative values. So in vertical value means it's like updrafts, whereas in the western part, like southwest and northeast part, you can see there is a downdrafts here. So most of the pollutants, this result tells that most of these pollutants will enter from the the east part of this anticyclone, that is head Bay of Bengal. In general, you can see that from 70 to almost like 100-degree east, this completely stretched with the updrafts. Whereas in the western side, you can see the downdrafts. So any air, the pollution entering into this, they can be pulled down to in the upper troposphere or the troposphere using this background vertical velocities as a tracer. This tracer as through the vertical wind. Now, then we move to see that long-term trends, whether we have seen this almost like more than 16 years data is available. It's the Calypso data from 2006 to 2020 we used here. Since the aerosol extension, we give the profile. Then we separated the aerosol extension. The below boundary layer, we calculate the AOD from surface to the 1.5 kilometer. Then 1.5 to 8 kilometers, we integrated the aerosol extension to get the AOD in the mid troposphere. And here we show from 8 to 8 kilometers that upper troposphere and lower stratosphere AOD calculated from the extension profile of the Calypso. And again, we divided the 4 lines represent the 4 southeast, northeast, northwest, and southwest part of the asthma region. Here, it's very interesting to see that there is a decreasing trend in the aerosol in the boundary layer, but more decrease you can see in the mid troposphere. whereas that increasing trend in the utilized region you can see very clearly. So this tells that in the changing climate, more and more convection is being happening. That is, again, you can see that vertical wind as a proxy. You can see in the right side we show here that there is a strong increasing trend in the vertical wind, means more abrupt in the recent decade, and that is making more pollutants enter into the utilized region. That's why we can see the clear increasing trend in the upper tropes and lower stratospheric aerosol concentration we can see from this plot. So this tells that there is because of the changing patterns in the global or warming climate, and that is going to affect these our utilized trace gases or the aerosol being transported from the troposphere to the utilized region. Then, in fact, all this what I mentioned so far is basically from the satellite measurements, and one must be cautious because the satellite measurements cannot be used as a means they cannot be treated this should be treated as a caution because the as I mentioned the cloud cover will be very high and many of these satellites will fail to penetrate even to the surface during this monsoon season. Then we thought that whether we can do the institute measurements to get more faith on that. So before that, as I mentioned in the aerosol from the Calypso also, we could see that there is a strong investment in the asthma region in the aerosol wax scatter. This is scattering ratio between 1.1 to 1.2 is shown here. And this can extend right from almost like 20 degree or 30 degrees to 120 degrees. And this is the latitude variation average between 5 degree to 105 degree east. You can see that the the uh, the the Asian summer monsoon anticyclone aerosols can reach even up to the Gadangi. Gadangi is shown in this lower uh, rectangle box, and this is from Hyderabad, and the top one is from the Varanasi, BHU Varanasi. So these are the aerosols. Again, the caution is advised because these are all from satellite. First, we have to make sure that these are really the aerosols or not. So then we thought that NASA has come forward, thanks to Dr. Jean Paul, who they came forward to have a campaign, that institute campaign to check whether really these are aerosol. If at all these are aerosol, what are those physical, optical, or chemical properties? Because unless we know the chemical properties, we cannot go for the radiative forcing estimates due to these pollutants present in the asthma region. So first and foremost, this campaign is, in fact, we have made an agreement between ISRO, NASA, and NRL as a nodal agency, and we have conducted a series of balloon flights from these three different locations like Gadanki, Hyderabad, and Varanasi. And these are the following objectives. First of all, we want to confirm whether these are all aerosols or not. Then, if at all is an aerosol, what are those physical, optical, and chemical properties, and how they are reached there, or whether any in-situ generation are transported from the lower atmosphere. Then, finally, to estimate that impact of regional global climate, because these are going to persist for more than 3 months once entering into this asthma region. So then quickly move to that one. So now this we call that asthma atoll, aerosol layer we call as an atoll, is an Asian tropos aerosol layer. Then from the satellite we have seen the discovery from atoll by Jean Paul. Then we move to the balloon campaign, then we call as balloon measurement campaign of atoll. This figure is shown, is taken from Tata Institute for Fundamental Research Balloon Facility, where this kind of very huge balloons we have flown that with carrying a payloads of almost like 30 to 50 kgs of payload, because I'll be touching upon what are those payloads we have taken to the utilized region in the next coming slide. So these are the three different places. For example, I show that Gadangi, Hyderabad, and Varanasi. These are three places. You can see that the balloon trajectories. We allowed the balloon to float, particularly from Hyderabad, almost like 2 to 3 hours to collect enough aerosol samples from here. And we had another campaign at Kaust in Saudi Arabia. Of course, we have not participated directly, but these three campaigns we participated directly. You can see that how the balloon preparations, even recovery. In fact, I can see that my photo I'm looking young in last 7, 8 years back taken, and Jean Paul is here, Amit Pandit and Ravi Kiran, and some of our colleagues are already students are here. Now they become faculty at various places. This is the, in fact, the well-settled people from our group. Then quickly move to that. What are the payloads we carried in this campaign? In fact, we want to make sure that each and every small aerosol, because we are looking into utilized region where the large size aerosols we cannot expect at that altitude. And for example, if there is a gas to particle formation also, we cannot expect a big size. So our instrument should cover very, very small to measure very small aerosol right from 7 nanometers onwards. We have taken care. And that maximum it can cover up to 100 micrometer. You can see that there's a different class of instruments we use, that mixing condition nuclear counter, where it can measure the size from 7 nanometer onwards And we have another OPC, which is 8-channel OPC. It is a size segregated. We can make it a size segregated aerosol concentration. We can measure using this thing. And for this MET1 OPC, in fact, basically it measures from ice clouds and microcop also, right from 1 micrometer to 100 micrometer. And there is another instrument called Cobalt. This can give the right from almost like 0.5 micrometer to almost like 100 micrometer. So this is the instrument where it can sense both aerosol and cloud together. And these are the instruments where only cloud sensor, and these are the instruments where it can only sense the aerosol. So because these are all very heavy to carry, and in this slide I am just listing that what are the payloads, so that we'll understand what different parameters we are going to measure. You can see that these are all more than 20 plus payloads we have kept, and the color which is put it in the red color are from NRL, and in the black color is from the NASA. You can see that mostly that NRL payloads have the background meteorology and dynamical parameters, including the trace gases like ozone and water vapor. And this cobalt also we obtained from the ETH Zurich. And we have also carried out the cloud particle sensor, microspherometer, PM sensor, and QCM developed by TFR Bell University. In fact, more important among all these things is the chemical. This is the aerosol impactor. This is used for the chemical component. This is one of the most important instrument when compared to rest of the instrument. So if you count this with 20 plus instruments to carry, almost it will reach to 50 kg, and in fact, not normal balloons cannot be used. So we used different types of balloons. We call the light flight, if it is less than 1.3 kg, medium flight, we don't need to worry too much about this one. But more important, in fact, we have carried more than 30 kgs of this payload. And one important balloon is the zero pressure balloon flight, because we want to collect the air samples from utility region by flying more time. So we should be able to make the altitude. We make sure that altitude will not be changing, and we'll always sense the aerosols from the desired altitude. So this is one of the important balloon flight we have. So then, as I mentioned, that first and foremost is to verify whether what we observed from the calypso is it aerosol layer or not. And here we show that over the two locations, the left panel is from the cobalt average of 5 flights over the Tuval, that is Saudi Arabia, and the east plot is from Gadangi and Hyderabad, where 12 flights of cobalt data has been averaged. And you can see that the red curve shown in both the panels are from the calypso. A very good consistency between the satellite and the instrument measurements observed. And this is one of the first and foremost objectives fulfilled, that whatever we observe from the calypso, these are all from aerosol, but not from other like generally we thought that clouds can have the cirrus cloud can also enter it as a aerosol. That is some confusion will be there. But here we make sure that this is very clear aerosol concentration. You can see that enhancement between 14 to 18 kilometers. You can see at both the altitudes. And the temperature part also we show that is where the coldest tropopause altitude. See there that you can see that enhancement in the aerosol layer. Then we thought to have the physical and optical properties, because once we know that, and also the number concentration. Here we show that in the left panel that different sizes, like right from 0.075 micron to the almost like greater than 0.5. You can see that this is the black color is from very, very small size, whereas the blue color is from greater than 0.15, the green color is 0.25, and red is 0. You can see that when the size is lower the size, higher the concentration we see. As in fact, this is what we expect at utility region. And there is an option in this optical particle counter that we can heat the air sample before entering into this filter, size segregated filter. And then we can heat that samples up to 180 degrees centigrade to see that how volatile that air sample we are making at this. And we can see that 60 to 80% this volatile nature is seen. And this volatile is partly due to that. You can see that in the lower panel, the enhanced water vapor, because as I mentioned, the tropical convection can reach to the altitudes of utility region. Then enhanced water vapor can enter into this one. And any gas to particle conversion with an enhanced water vapor can lead to the aerosol new particle formation. This is one of the clue we get from these kind of things. You can see that even in the cobalt backscattered profile, there is strong backscatter is there, that is nothing but is related to ice cloud. Whereas in the weak scattered, we see just above the ice clouds is the aerosol. Then, as I mentioned, and we have for every almost 92 flights, we have in that more than 50% we have calculated the size segregated aerosol number concentration. And this figure shows in 2018 all those flights which we got the particle concentration right from surface almost 30 kilometers. You can see there is enhancement in up to 5 kilometers. There is sudden decrease after that. Again, in the Atal region from 14 to 18 kilometers, you can see that enhancement in the number concentration. And there is a broad maximum here that is nothing but we call as a Jungi layer. It's a public called as a Jungi layer. And we make sure that whatever we measure that are all well calibrated, and we do not make any mistakes in the measurement, and the right thing will show that within the 10% of consistency of the measurement, we could able to get these things. Now, then as I mentioned, that the chemical composition is very, very important, and we use the zero pressure balloon flight. In fact, I do not have time to explain this one, but somebody interested to go through this in publishing BAMS, where we use the zero pressure concept balloon, and this is a plate of plastic, and it will not see there is a two things. One is the outlet will be there as a wall, and there is a ballast we carry that you see, and any once it reaches to some desired equilibrium level, and if suppose if because of contraction or expansion of the air inside the balloon try to come down, or it will enter into the wall, but if it is still come down, then we release the ballast so that it will make lighter, so that it will go up. This is the way to systematically maintain that desired altitude that balloon is flying, so that the air sample which we collect from this is not contaminated by the background atmosphere. So basically, this we use the aerosol impactor. This is a four stage impactor. The first stage is will allow the greater than 1 micrometer will be filtered here, and the 0.25, 1 micrometer will be filtered in the second stage, and the lower the size will filter at third, and the lowest size will be filtered at the fourth stage. So that air will be entering into this and will be going, and at a constant pressure will be having this air sample, and this is the duration of the flight. You can see that almost like more than 200 minutes we allowed the balloon to float, and so that enough air samples being collected by the impactor. And once the air sample is being collected in the impactor, then we have sent it to the IC analysis. Thanks to Dr. Neeraj Rastogi from PRL, who has done this analysis from the PRL. And before launching this impactor in the balloon, we make sure that this has been run on the ground, so that we will get the ground concentration. What are the major things? And this is shown in this part. You can see at the ground that major concentration like sodium, chlorine, and these are the major, and sulfates are dominant as expected during the monsoon season. But if you see that ZF2 and ZF3, these are long duration flights which we flown in this region. You can see instead of sulfates or sodium or chloride, we could see that there is a nitrate are dominant. This is very surprising, because we thought that in the stratosphere, this is mostly the sulfates are dominating, but to our surprise, we could see that nitrate and nitrites are more concentrations are very high. In fact, we made sure that the wall of this impactor will open only after reaching the desired pressure level of 200 hectopascal, so that there is no contamination of the tropospheric air. And also, while coming down the balloon, it will stop. That wall will be stopping at 200 hectopascal, so that that no air will be contaminated from the troposphere. And lot of care has been taken before reaching to these samples reaching to the PRL. And thanks to Dr. Niroji for making this analysis. Then, in fact, when we confirm that nitrate and nitrates are dominant particles, we are a little bit doubt, because whether we have done any mistake. But again, we are so confident to see that the similar result from the statistical aircraft campaign. They also could see that nitrate and nitrate are dominant particles. Then we got a very good confidence that we are the first to report that nitrate and nitrate containing particles are dominating in the Atal region. And then what makes, as I mentioned in my previous slide, there is a Jungi layer, because the broad maximum Jungi layer. But what separates the Jungi layer and Atal? This is one of the important aspects which we have dealt. And thanks to Dr. Akhil Raj, who has done this analysis, you can see that in the left panel, this Atal, you can see the enhanced backscatter ratio, and there is a well separated and around 18-19 kilometers, where there is a minimum in the aerosol concentration backscatter. And after 20 kilometers, you can see that again enhancement is this we call popularly called a Jungi layer. And because we are getting from this Atal region, you can see that sulfates will be dominating in Jungi layer, but not Atal is completely different. And what we found is nitrate and nitrates are dominantly. Then what separate this one? And this, in fact, there is another innovation has come from the Sunil Kumar et al., who has given a new definition for TTL based upon the stability of the atmosphere. Here we show the temperature profile, and the second panel show the potential temperature profile, and the third panel manifest frequency. And you can see that the maximum gradient in the potential temperature, you can see around, we call as a L max, and that is matching excellent with the top boundary of the Atal region. And you can see that the various tropical tropos, earlier people used to think that from the difference between convex to offshore level and pole point tropos is the TTL. But with the new definition given by Sunil Kumar, that is from convex to offshore level to the level of maximum stability. And this definition matches well with our understanding, I mean, so that Atal region. So that it very clearly shows that the Lmax will be the upper boundary of this Atal region. Above that, it's we call whatever we see the aerosol layer is the Jungi layer. Then we thought we thought whether only for the particles this will be the difference between Atal and this is there, or even for the trace gas also is there. And you can see that in the second panel. This is the first panel is from the aerosol. You can the enhancement in this one, and is exactly matching with the inversion, the Lmax here. And the middle panel is shown for the water vapor. You can see that there is a secondary maximum in this water vapor. So, and there is a minimum after this one. So, for even for water vapor, the same definition that Lmax is the top of the Atal is matching very well. But again, for coming to the ozone, the top of the Lmax is not the gradient in the strong gradient is seen. So we feel that if you want to see that trace gas like ozone, this top of the Lmax is the definition is not working because perhaps because of photochemical reactions lifetime of trace gas we need to consider rather than just a particle or the particles which we consider as an aerosol in this Atal region. So this tells that one can see that enhancement in aerosol in the Atal region and also that enhancement in the water vapor. And even if the trace gases like any trace gases entering into this one, gas to particle formation will be there, and there is a chances of new particle formation. In one of the battle campaigns, we could able to see very clearly that the indication of new particle formation, and this figure shows from the particle optical counter, the OPC, and the size segregated again. You can see that the concentration right from 0.05, where you can see that the black line, and to the 0.5, is the red line. You can see that suddenly in the almost reaching up to 16 kilometer, there is an enhancement in the concentration. You can see. In fact, these are all not transported from the down because if it is transported, you can expect more concentration even at mid-troposphere like that. But maybe perhaps one reason that once it enters the Atal, it will persist for a long time. But these are all like it's measured at instant of time. So this tells that a clue that the enhancement in the small size particles suddenly tells the clue that there is a secondary aerosol formation at this altitude. These are all first cut results, is still not yet published, and Vernier is working on that this aspect. Now coming back to the summary of these the campaigns which we conducted from 2015 to 2020, 92 flights were flown, and we could able to confirm that this Asian tropos aerosol layer, which is discovered from Calypso, is basically the aerosol layer. And we also got all optical, physical, and chemical properties. And more important, that chemical property tells that is nitrates are dominant rather than the sulfate, which we expect in the lower stratosphere. And after that, we stopped because this was the implement agreement was finished at 2021, and the COVID time was there, and we could not make much progress during that time. But we entered recently in the last month. We entered into the second campaign, the 23 to 27, and this year, this time we are going to have different. While confirming the earlier measure, we want to have little differently, and this time we want to get the long duration flights by launching these balloons from Andaman Island, so that we can cover those payloads in the mainland. And the new sensors we want to use for the chemical component because there is a doubt exists still because how clean we are bringing that samples from Uterus region to the troposphere and we are analyzing. So little doubt always persists. To remove the doubt, we are going to use the new sensors for this one. And more important, at the same time, there is another campaign by French team in collaboration with NASA. They have done Stratral 2 campaign where they have launched the similar payloads what we used in the battle. In fact, 90% of those payloads are same payload they use in Stratral. And the beauty of these Stratral campaigns is that they launch the balloons, the long duration balloons that we call super pressure balloons, and in 90 days they can circumference the complete globe. So by measuring the in situ measurements, you can imagine that same measurements we are getting in situ every 1 second being measured and stored in that, and almost a complete covering globe we can able to get this kind of measurements. And again, there is one campaign that called Eclipse campaign that NASA has done over this part of the region in the eastern part of India, covering from Japan to this part. And this campaign also conducted in the last year in 2022, and it has carried a similar payload. And this data is open now, and I suggest many of you people can go through this data set And I think by making the synergy of all these measurements, we can do some wonders. Now, and what I presented so far is has been appeared in these 9 papers. If anybody interested, I can share all these papers so that you can get much detail, much deeper understanding what I present in the last 45 minutes. So I would like to summarize. And first of all, we have concentrated more on the asthma, that Asian Summer Monsoon Anticyclone. In fact, people working in the aerosol field, they will forget about the background dynamics. And I want to emphasize that dynamics plays a major role in any modulation of these trace gases or aerosols, right from surface to the utilus region. And any variability in these asthma is seen in the trace gas and aerosol. And we could see the large spatial asymmetry in the aerosol and trace gas within asthma. And we got all the required information for radiative forcing estimates, like trace gases, aerosols, cycle aggregation, and all this. But we have not done the radiative forcing estimate so far. And this is what we were going to attempt very soon. And our student is working dedicated. Our team is working on this aspect. And in fact, because this is persisting for more than 3 months, it has a lot of impact on regional weather and also because climate, because almost it extends a 120-degree longitude band. So, and persisting from 10 to 15-degree latitude and 100 degrees longitude. So it is definitely going to expect a background. It is going to impact. Also, we can expect a change in the climate because of these trace gas and aerosol present in the asthma. And more important, the chemical properties they get first get chemical properties we could get, but long way to go because we had so far only 2, and we need to get more. And the aircraft can give better insight because it's the real-time analysis we can make through aircraft. And now more challenges are entering because while forest fires or volcanic eruptions are throwing a new challenges. In fact, you can see that the Canadian fire and Australian wildfires. In fact, these are huge. They have ejected huge of these trace gases into atmosphere. And recently, in the right from 2020 onwards, we have witnessed several volcanic eruptions, and these are also going to affect our UTLS composition and also in turn and asthma, and in turn again in the atoll or whatever we call the asthma region trace gas pollutants. And a lot of efforts need to be kept to make a synergy between different campaigns conducted so far. For example, Stratoclone, Battle, Eclipse, and Strato2, and most of the data is available freely. I suggest that research scholars who are attending this talk can have access to these different data sets to see what are the missing elements so far we attempted so far. Of course, for the vertical transport and long-term transport need to be quantified because there is always a blame over countries like India that though looks like a strong aerosol layer sitting over India, it doesn't mean that we are polluting that one. It can enter right from it can be either due to vertical transport or long-term transport. That has to be quantified first. And I think modeling and simulations will help in this aspect. So with this, I'll stop my presentation. I'll take some clarifications or questions if anything. And again, thank the team for making me to present in front of you today. Thank you very much.
Thank you so much, Dr. Ratnam, for such a nice talk. Now I would request Dr. Padma to handle the question answer session. Dr. Padma, I'm sure there will be many questions and Dr. Padma will be handling that.
Yeah, thank you, Dr. Neeraj. Yeah. Thank you so much, Dr. Ratnam.
Thank you.
And we have some questions we can take now. I don't see anything in that chat box. I think, Dr. Neeraj, could you see anything in the chat box?
No, there is nothing in chat box, so we can directly take questions from participants.
Okay.
So just I wanted to, if the chair's permission, I wanted to appreciate Dr. Ratnam for his excellent talk. But of course, he talked about many aspects, particularly UTLS and asthma. Of course, we have been talking all the time. Our main aspects of global warming and climate change, all these things, only our surface level measurements are enough. It's not. Because surface level measurements, because they give the source information, they are required. Not only that, we require the vertical distribution. That's what I always emphasize. See how many critical, how many very detailed information is coming from the vertical distributions of either aerosol or gases, whatever they want to talk. So he emphasized a lot how many things have come out from the observations of vertical distributions of aerosols and gases. But of course, that is one real appreciation I wanted to make on Dr. Ratnam's talk. And of course, asthma is a special event he was talking about. I'm talking into the vertical distribution. And one more thing, Dr. Ratnam, you have talked about Atal. Like in our tropical tropopause, you have there also thinning of tropopause, double tropopause, this type of aspects, see, or no? That is one thing I wanted to know from the speaker. And my basic question was, when we are talking about the wind field, always the question comes that background wind field, whether how you have controlled that, have you removed that background variations while talking about the real observed wind field? That is always a question. And another thing is, of course, this is a purely statistical point of view. End point effect in trend estimations. You have talked about long-term trends also, of course. In the latter part of your talk, you have not talked too much about trends, but you have shown a couple of diagrams where the long-term trends in extinction or whatever aerosol or gas concentration are. But always there is another problem, universal problem, end point effects. In your time series, always the end points will always change the entire trend. How do you control that? How do you control that in your trend analysis?
Sir, you're putting so many questions. I'll answer one by one because I'm very poor.
Please.
I don't have that much.
It's not like that.
But I'll try to answer your questions.
Sure.
Coming to the last question that you mentioned, that is the end point, starting point, end point, that linear trend will give that increasing or decreasing trend. In fact, we have used that multi-regression analysis.
Okay.
I have not shown here, but in many of your papers I can send to you. We have not depend on the linear trends. This multi-regression, what it does is, because we are talking, when you're talking about the only surface, this linear trend will work, though it depends upon starting and ending point. But suppose if you want to have vertical distribution, when you're talking about trends, you should take care of those, as you rightly mentioned, that background wind fields are going to create a lot of problem, because it has semi-annular oscillation, quasi-biennial oscillation, ENSO, even solar activity. So these has to be removed if you want to see real trend. In fact, we have done that. In this talk, I have not projected. I can send those papers to you. After removing all those background thing only, we consider that as a true trend. That is first part. And the second thing is, sir, so far, whatever the people are using, means particularly for aerosol and trace gas people, they never take, and in fact, they will forget about the background conditions. As you rightly mentioned, background conditions are very important. See, what happens, for example, that asthma, they feel that Atal is a permanent feature present in the uterus region. But according to the asthma variability, these variabilities also vary. So those things we have considered very clearly by considering the dynamical aspects of those background conditions in this one. And I have not shown the later part, the long-term trends, because the later part of my studies, these are all balloon related. And though we have done for 92 flights, they're stretched over 6-year period, this is not enough to have any long term. And that long term can be data, trends can be made from the satellite measurements, where we have almost like 2004, 2006. For example, MLS data from 2004 or Calypso data from 2006, we have covering more than 15 years of data. Those data sets we have used for trend analysis. But before taking trend analysis, we want to confirm that whatever we observe from the satellite, because we cannot trust the satellite, we cannot take blindly whatever it gives, whether it is coming. So our later part of our interest is to confirm what we observed from satellites. And once we confirm, and no satellite data will give the chemical properties, and this is what our main interest, to see the chemical properties of aerosol, in addition to the trace gases, which are very much required for radiative forcing estimates. So this is our total way we approach. Of course, the trend is very important, but whatever the data we have, particularly for vertical distribution of aerosol trace gas, the data availability is not sufficient.
Okay, nice. Of course, you have long back observed these drawbacks, and then you are rectifying one after the other. Okay, but ultimately only one question. You have done not only the surface level, but also the higher levels like UTLS, where the mixing and then transport of aerosols or gases are very, very important.
Yes, sir.
But what is your ultimate opinion, whether these aerosols, whether you call them as positive pollutant or negative pollutant, what are their effects on your monsoon precipitation?
Yes, sir.
Whether it, what is your
In fact,
expectation after analyzing so much data?
yes, sir. In fact, I should recall one of the works done by Swarna Fatnavis from IITM. She has done some modeling simulations, and she could see that the Atal, how it is going to affect the monsoon system, particularly she has shown that during the this aerosol can create a drought during the monsoon time. She has shown some couple of papers she has published. I can send those things for you. In fact, it has a lot of effect on monsoon circulation.
I know. But of course, you have rightly pointed out, see, not only the microphysical and then radiative properties, but chemistry is very important there. See, because refractive index or chemistry related chemistry,
You're right.
related chemistry only can clarify you whether a particular aerosol enhances the or encourages the precipitation or discourages or diminishes the precipitation.
You're right, sir.
Similar case with trace gases also. So I think this I have been seeing, looking for long time. If somebody can come out with long-term data and then show systematically this type of aerosols over particular region, they are anti, they are pro for the monsoon precipitation. So that is a great research, I feel. And then now you have brought out once again, I appreciate your talk, because it is not limited to only surface level or few meters above the ground level. It is all the levels even up to stratospheric altitudes. And there so many transport phenomena in between are acting on the monsoon precipitation. It's really very good talk and exciting talk. Thank you very much, Dr.
Thank you, sir.
Thank you so much.
Any more questions?
May I?
Yeah, this is Ramana from NRSI. Can you hear me, please?
Yes, sir.
Can I ask?
Yeah, please proceed, sir.
Dr. Ratnam, very good presentation here. I really enjoyed it. And I would like to discuss rather than asking a question. You have shown when you are explaining that the ASMA aerosol distribution, there you have shown U component of the wind. If you can go back slides, maybe fourth or fifth slide, I don't remember. We've shown the trend increasing, and interestingly, yes, I think this is the one. You see that minus sign is changing to the positive sign.
Yes.
If it is easterlies are changing to westerlies, maybe. So if the easterlies are changing to westerlies, means your total the core may be shifting towards southern part of India, means equatorial region. Otherwise, you should have been getting easterlies. Whereas you are getting westerlies means it is shifting towards, towards the equatorial region, means total core may be sitting over India, if I understand it correctly, based on U component of the wind.
No, sir.
Discussion here is, yeah, please.
Can I clarify? In fact, if it
my
is
discussion here.
Tell me, sir. Please.
Yeah, please go ahead. Please go ahead.
See, in fact, what I want to mention here, you see the right panel that tells the trends in the geopotential height. You can see that lot of trends in the north part of that asthma. I mean, geopotential height is changing, but not in the southern part of India. I mean, you can see that east, west, and north part is. So this tells that in the changing climate, the extent of that asthma is going to increase. Not the extent the tropical latitude, but towards
your U component, if you see from
but U component will tell only east and west, not the north and south.
Yeah, that the belt is shifting towards India.
No, sir. Here, the U component will tell east, region. No, U component will tell east and west part, west component, not the north and south. You have to show that the meridional wind.
Sir, this is only zonal part of the wind.
Okay,
And then plus minus that polarity indicates the updraft and downdraft.
No, sir. No, sir.
No?
No. See, minus in zonal wind tells that it is a westward.
Westward.
Plus means it is eastward.
Okay.
In the vertical wind, minus
So
in the
what-
pressure.
this
pressure
is-
will have, yeah.
So this is the average taken, or it is over particular location? I'm only referring to the total bottommost.
The
U
bottommost
component.
is the yearly average. July, August, that yearly average.
Over,
Every year,
over a particular region, or
No,
it is a sum of
this
the
is
complete core?
No, this is a complete asthma region. 16.75 geopotential height.
Above 16.5.
See, for example, here 16.75. In fact, this is the region. 16.75 is the blue color. It's the top left panel. This represents that asthma region.
The total region you have taken and then taken the average.
Exactly.
Annual average.
Yes.
And then, if I understand, your westerlies are becoming easterlies. Means direction is also changing and magnitude is also
East-west
changing.
asymmetry means changing. This figure does not tell the north-south component.
Yes. But yeah, okay. If I ignore it, okay, it is. I'll rephrase it like this. I'm sorry. Your wind direction is changing. Easterlies or westerlies are becoming, and magnitude is also changing. This can happen if this is from model output, right?
It is a model.
Okay. So there are two things here. One is easterlies and westerlies are changing, means becoming, one is becoming, another one means your north-south temperature gradient is changing. That only can cause this direction change.
You are 100. Yeah, you are right.
That is one thing. And the second thing is whether it is correct, because it is a model output.
No,
whether it is correct.
Sir, we
So,
have what we have.
One minute, please. I'm not doubting here. I'm trying to help you only.
Okay.
If you see the satellite data, any of the satellite parameter, take it as a proxy and test it and say satellite data is confirming this this observed thing, whatever you are saying, then or it is something else. So this is something, if you can.
No, sir.
No?
To my best of knowledge, no satellite exists to view the wind at these altitudes. First thing. Second.
Not wind, any other proxy, like any other tracer or something you
actually,
take.
We verified with the ground
and see whether.
We verified with radio sonde. See, in the asthma region, for example, there are several radio sonde stations here, and this asthma is close to 100 hectopascal. We verified with radio sonde data, long-term data, 1980 onwards we collected, and we have seen that the similar variation in the radio sonde data also.
Then I think you have a good thing to show south-north temperature gradient.
Yeah, actually, one of the papers we have included that also, because any change in the north, the gradient between land and ocean, that is going to strengthen the monsoon circulation. Indirectly tells that.
Yeah. So if you have that paper, can you show?
Yeah, I will share it.
Thanks a lot. Yeah. Thank you. A nice presentation.
Thank you.
Thanks.
Any more questions from the audience? Yeah, Dr. Ratnam, I have one question. Not question, just one small
clarification.
Yeah. So regarding that battle experiment, it looks very interesting. Like, so I mean, usually during which it is operated during monsoon period or at any other part?
Actually, this battle campaign, we generally because as I mentioned, July August is the peak period. So and over the asthma region, particularly if you want to concentrate on that region, best season will be the August.
Okay. So, I mean, you'll be looking for the break monsoon period or during
No, we don't look like that. So what we do, they generally from July 15 to August 15, we'll plan every alternative day. We'll have the balloon campaign.
Okay.
Irrespective of the activity, because we need to segregate based upon the activity of the monsoon. We have to segregate how these trace gases or pollutants are changing. That is our motto. So generally we'll plan a month-long campaign over Hyderabad. I think you are going to add a very good thing from the Bhopal test bed.
Yeah.
If you have that the drone-based LiDAR, I think it is going to add a lot for this kind of campaigns. Even radar also is very good. You will have the winds up to 20 kilometers.
Okay.
So background meteorology dynamics and including the aerosol part, you can take we can have very good understanding from the Bhopal, your test bed from IIT. Next time, I think we will include your team also whenever we'll have the such campaigns.
Yeah, sure. We would like to actually.
Fine.
Yes, yeah. And any idea about the future battle experiment?
Yeah, actually now it is because of COVID, we could not have done in 2020 and 21. And at that time, we have that implement agreement has expired. Now we have signed again. From this year onwards, from 2024, actually we want to have one pre-monsoon campaign. Discussions are going on before starting actual campaign in July August 2024.
Okay. Yeah, you please let us know.
Yeah, definitely.
Yeah. So, any more questions?
And
I think there is
Dr.
something
Sheni.
from someone.
Sheni Tiwari.
May I?
Yeah, please.
So, Dr. Ratnam, first of all, very thank you for such an interesting talk.
Thank you.
And it's not a question, it's just a small query regarding to your experience, what you get during this campaign. So I just want to know, what is the role of vertical wind propagation aerosol in the coupling of stratosphere and troposphere?
It's very strong, sir. For example, if you see my first part, see, this figure tells this is the vertical wind. You can see that this part, bottom right. This is from model, but there's the pressure vertical velocity. And you can see that over this latitude band, completely that updrafts in the southeast and southwest. So any particle entering into in the boundary layer can take, those particles can be transported to upper troposphere or even lower stratosphere. That vertical wind has very, very strong role in transporting the lower atmospheric pollutants to the upper atmosphere.
So my concern, well, my question in other words, like once it aerosols is coupled, so what is their role in the coupling of stratosphere and troposphere?
Once it enters, see, for example, that east part, you can see that this green color, that magenta and the black color. This is east part. If you see the north part, there is a downdraft. So aerosols entering or the trace gases have entered in the asthma region, they can be brought down also because of this downdraft. So in this case, what we expect is the air entered into asthma can be brought back into the upper troposphere through these downdrafts.
Okay, thank you.
Any more questions to Dr. Ratnam?
I think I'm clear. So there's many small questions were there and few questions were there.
Yeah. So if there are no more questions, then I'll proceed for vote of thanks. Yeah. So on behalf of ISTA Executive Committee, I would like to thank Dr. Venkat Ratnam from NARL for a very interesting and very informative talk on aerosols and trace gases, their trends and variability. And he had indeed given a very detailed explanation for each of the instrumentation and their operation, and more interestingly, various field campaigns conducted were nicely brought out. And then, battle experiment seems very interesting to understand the vertical distribution of aerosols and trace gases, especially during the monsoon season. And I'm sure now many students and researchers working in this area will approach you very soon.
Thank you.
Yeah. And many, my whole team is sitting with me. So they're all excited about this experiments which you have shown. Yeah. And I also thank the audience for their for following up ISTA monthly lecture series and their very active participation. And I thank Dr. Devra and Dr. Ramna, who also actively participated in this lecture series. And thank you all. And finally, I wish you all a very happy New Year. Thank you.
Oh,
I think this is the last lecture series in this year.
this year, right.
Yes.
Wish you happy New Year to the entire team.
Thank you.
Happy New Year to
Thank
all.
you. Thank you.
May I leave now?
Yes.
Thank you.
Thank you.
Thank you, Dr. Ratnam.
Thank you. Thank you very much.
Thank you. Thank you.
Thank you so much. Bye.
Thank you.